Welcome to the video lecture on support vector machines in the linearly separable case. Support vector machines, shortly known as SVMs, are popular for the better generalization on unseen data. In this video, we will see the formulation of SVM objective functions and also how SVMs are better generalize the data compared to the other linear classification models. So in this lecture, we will see briefly about the linear classifiers and the decision boundary that is formulated. And then we will discuss about margin and the maximum margin. Then we'll talk about the linear SVM and the associated objective function. Then we will close with the conclusion remarks. So along with that, we will discuss about how SVMs can be implemented for the classification. So using some hands-on. So consider this data. The data here is belonging to two different classes. So this data is belonging to the positive class and this data is belonging to the negative class. And now how this data can be classified. So now we can understand that it is possible to use a linear boundary to separate the data with zero error, right? So this data is basically linearly separable data. And how would you classify this kind of data? So because the data is linearly separable, we can use any of the linearly classification techniques. We can use any of the linear classifiers such as logistic regression or the perceptron to classify this data, right? And the objective of these linear classification models is, so they find a mapping between the input data and the ground truth values y. So F is basically a function mapping between the input data and the ground truth. And F is a function on the input data x and the parameters w and b. So we can take the decision as based on the sign of wx plus b. So if this wx plus b value is positive, then so we can assign the example to the positive class, or otherwise we can assign the example to the negative class. So such a decision logic we can formulate. And now let's assume that we are applying one of these linear classification models and we are obtaining a boundary which is linear. So here in this case, assume this is the linear boundary we obtained. And we can see here, this boundary can separate the data with zero error on the training data. So this could be one possible boundary. And now let's assume that this is the other boundary. And this also could be another possibility, right? So depending on the initial values, so we are taking for the W's, so that the boundary will be changing. And all these three are the possible decision boundaries. And we very well know that in case of the perceptron, we can obtain the boundary with a zero misclassification error because the data is linearly separable. And now we understand that there is a possibility of having multiple boundaries in this case. And consider this now. So we have multiple such boundaries. Any of these boundaries can be used to separate the data with zero error on the training data. So not only these possibilities, so we can even draw infinitely many boundaries in between these classes such that the data can be classified with zero error. But which is the best decision boundary among all these possible boundaries? So with common sense, we can understand that so the one which is exactly in the middle or the very far from each of these classes, so can be the best boundary, right? So the one with the maximum far from either of these classes or the boundary which is maximum distant from either of these classes can be considered as a best boundary because that will be having better generalization on the unseen data, right? So, but before trying to understand how to get such a boundary, so try to understand what a margin is. So we understand that this black line is the decision boundary between these two classes. Then when we extend this boundary, so towards the positive class, then before we hit the data point, so till here we can extend the boundary, right? So that is the orange line. And towards the negative class, if we extend this boundary till here, we can extend the decision boundary, right? So such extension of the boundary till we reach the data points of either of these classes. So that width is the margin between the classes. We can define the margin in the context of the linear classifier as the width of the boundary, so which could be increased by before it hits any of the data points. in the training data. So that's what the margin is. And then what we are interested in, we are not interested in simply a margin. We are interested in the margin which is of maximum distance apart from each of these classes, right? So such a margin is known as a maximum margin. Then what is a maximum margin classifier? So here we are discussing about the linear classifiers, right? So in the context of the linear classification models, the maximum margin classifier can be defined as any of the linear classification model with the maximum margin. If you observe, so this is having the maximum margin. So such a boundary, such a margin is known as the maximum margin, and the classifier which generates such a margin is known as a maximum margin classifier. And one such, the classifier which can generate such a maximum margin is the support vector machines. And we call this as linear SVM because, or shortly we can call it as LSVM, because so we are trying to obtain the maximum margin classifier in the context of the linearly separable data. And now consider on the margin, so on the either side, so on the boundaries of the margin, you can see there are some data points that are falling, right? So such data points are very, very important in the context of support vector machines, and such data points are known as the support vectors. Here, this is the support vector from the positive side, and these data points are belonging to the positive class, and this is the support vector from the negative class, and this example is falling on the boundary, so towards the negative side of the data, right? So these three are the support vectors. And consider, so how do we define the decision boundary and the margin? So consider this is the classification boundary, and this plane as the plus plane, and this plane we can call it as a minus plane. So what is this plus plane and minus plane? So here if you observe that all these examples that are in this region, so they are basically belonging to the positive class, right? So we can call this region as a positive region. And all these examples that are falling into the negative class, so that region is the negative region. And this minus plane is the plane, so which can be drawn towards the negative class, and before you hit any of the example of this negative class. So such a boundary is known as a minus plane. And similarly, so if you can draw such a boundary on the positive side, so such a plane is known as a plus plane. So pictorially, we can see here that how do we represent that mathematically? So that's what the question is. And when it is extended for multiple dimensions, like here in this case, we are seeing, so in the context of the two-dimensional case, right? But if we extend that to m input dimensions, so how do we represent this? So that's what the major question is. So now consider on the plus plane, if you observe, that is on this line. So here for any example, if you take x on the plus plane, so the value wx plus b is equal to +1, right? So this is the +1. And for any example x on the negative plane, that is a minus plane, so this value will be equal to -1, wx plus b equal to -1. And so with that notation, so we can use a decision logic as, so if any example x, so if wx plus b is greater than or equal to +1, then we can assign that example x to the positive class. So here you can see, so for all these examples, so on this line, for any example x, this wx plus b will be equal to 1. And for all these examples which are on the positive zone, so then for them it is wx plus b is greater than or equal to 1. So we can assign such examples to +1, that is to the positive class. And similarly, the decision logic for the negative class would be something like wx plus b is less than or equal to -1, right? So in that case, we can assign them to the negative class. And what about the examples that are within the margin? So for those within the margin, the value of wx plus b would be within the range of -1 to +1. So with this in mind, so let's continue with the notation. So let's assume that for the, let's continue the formulation of the maximum margin. Let's assume w is the decision hyperplane, which is normally a vector, and xi is the ith data point in the training data, and yi is the ground truth class label for corresponding to the ith sample xi. And remember, I value should be either +1 or -1. It cannot be a 0, 1. And the classification logic that the classifier is, so basically f of xi, So we can use a decision logic as depending on the sign of this W transpose Xi plus B, we'll be assigning the example to either the positive class or to the negative class. And then what is the functional margin for this example Xi? So we can define that as Yi into W transpose Xi plus B. So now keeping this in mind, so let's define the margin geometrically. So let's consider any example X, so which is away from the decision boundary. And now the distance from this example X to the decision boundary. Here you can see this is the decision boundary and this is a positive plane and this is a negative plane. Now this is example X, which is randomly chosen, which is away from the decision boundary. And now the distance between this and this plane would be R. We represent that with R. And how do we compute that? So, and here we can see W is a vector which is perpendicular to this decision boundary. And how do we represent that? So that can be computed using this, right? R equal to the Y into W transpose X plus B by norm W. And we understand that the examples that are closest to the boundary, so those are the support vectors. Here we can see this is the example that is on the boundary of the margin, and thus that is from the positive class, and these two are the examples that are closest to the boundary that are from the negative class. And these examples are known as the support vectors. And then what is margin? So we can define margin. So as we represent that with the rho symbol. And so it is the width of the separation between the support vectors of either of these classes. So now we know how to identify this distance. So basically this is R is the distance between this point and this, right? The hyperplane. And similarly, we can identify the distance from this point to the hyperplane also, and from the distance between this point and this also. So once we get this distance from the boundary to the closest sample of the positive class and the negative sample, then if we sum them up, so then we'll be getting the width of the margin, that is rho, right? Then how do we get that? So that rho can be represented as 2 by norm. So how do we get that? So how is it 2 by norm? So that we'll just discuss about it. So let's consider this one here. So let's assume for the sample on the positive side of the margin. So for this sample, what is R? So for this, the ground truth Y value would be 1 because it's on the positive class. Then W transpose X plus B, because it is on the boundary, that is a positive plane, this value would be 1. Then it is 1 into 1 by norm W. Then it will be the R value for this example associated with this example is 1 by norm. And similarly, for this example, the R value, associated R value would be 1 by norm. Then if you consider the rho value, so rho equal to 1 by norm plus 1 by norm. So it will be 2 by norm. So that is how we get the margin value as 2 by norm. And what is our objective function? So not only identifying the margin, so we are targeting for identifying the W with the maximum margin, right? So our objective is to identify the classification boundary with the maximum margin. So that is our objective is to maximize 1 by norm. So if you ignore the scalar, then it would be 1 by norm. So if we can better formulate it in the minimization terms, so then we can pose it as a minimization problem. So minimizing the norm W. So here we are maximizing 1 by norm. And instead of that, we can pose the problem as minimization problem, where our objective is to minimize the norm. So that is what the objective for our linearly separable data. So for the SVM in the linearly separable case. And because it's in the linearly separable context, we call it as linearly separable, linear support vector machine. And now how do we represent that and how do we solve it? So let's try to represent the objective function. So here our objective function is minimization of the norm W, and we can write it as norm is basically the inner product, right? So minimization of W transpose W. Here you can see in the objective function, we have the quadratic term, and when it is quadratic term, and here this is the objective function. So minimization of half into W transpose W, and this half is just for the convenience. We just included that. And then what is the constraint? Our objective is to obtain, our objective is to minimize this term. And under what constraint? The constraint is such that, so this condition has to be satisfied for every example. right? So yk into w transpose xk plus b is greater than or equal to 1 for every example. So instead of writing it as a sign, so we just changed it to yi, right? So instead of writing it as, so based on the, our decision logic is no more a sign of w transpose xi plus b. So now we changed it to a single decision logic. So under this constraint, so this objective has to be achieved. So then how do we solve it? So we cannot straight away solve it. So we can convert this optimization problem into Lagrangian. So here you can see the primal, this is the condition is a convex optimization. So here you can observe the cost function here is a quadratic in nature, right? And the inequalities here you can observe that convex. So the problem here falls into the domain of the convex optimization problem, which is more specifically into the quadratic programming, right? So this formulation of the problem is known as a primal problem in the convex optimization, in the context of the convex optimization. So now we are converting this problem into the primal form. So now we are converting this problem into the primal form. So here W transpose W. So this is the minimization problem, and this constraint we are changing that. So we are having the associated Lagrangian multipliers. So this constraint is changed to this term now, and instead of having the inequality, we change that to the equality sign. And then under the constraint, all the Lagrangian multipliers alpha case must be greater than or equal to 0 for every example, every kth example. And this should be satisfied for every example, right? So for every example, this yk into this term should be greater than or equal to 1. So that is how this should be satisfied for every example on the training data. So now this is the primal form of your objective function. And now this, the solution for this can be obtained by the saddle point of the Lagrangian. So it's a maximization and then followed by a minimization. So then how this can be obtained? So this can be obtained by taking the partial derivative of the loss function with respect to w and then equate that to 0, then we'll be getting the w's. And similarly, when we take the partial derivative with respect to b and equate that to 0, and this is what the condition will be getting, and this is the condition and this is the w value. So we are getting the w value, but the problem is what about the alpha case? So our decision logic is now, so basically it is w transpose x plus b and based on that sign, right? So now we are getting this decision logic. But so if you observe, the w is having some associated alpha keys. But how do we get these alpha keys? That is a Lagrangian multipliers. And to solve those Lagrangian, what we need to do is, so we have to consider the dual form of it. So now we have the w and this is the condition, and you substitute this w value here, and this is the condition along with this condition. So you substitute this w value here, here and here. Now we solve it. When we solve it and simplify this primal form, so what we are getting is a dual form. And now we can solve this problem using the quadratic problem. And now, so when we solve it, so we'll be getting the alpha k values. So now here you can see the dual form is straight away convex optimization problem, and we can solve it using the convex optimization problem, and then we'll be getting the alpha k's. Here you can observe the alpha case must be greater than or equal to 0 for every training sample. And once we get the alpha k values, we can obtain the w value. And once we have the w value, and our decision logic can be implemented. So what is our decision logic? So this is the decision logic. wxk plus b is greater than or equal to 1, then it is positive. Otherwise, it's assigned to the negative class, right? But what is w? W is summation over k equal to 1 to n alpha k yk xk. So yk is the ground truth, xk is the example, the kth training example, and alpha k is the associated kth Lagrangian multiplier, and we can solve it when we solve this optimization problem, right? So now we get the alpha case, then we have y case, x case, and then we'll be getting the w value. Once we have the w value, then we can apply it on any of the test sample. So during the evaluation, how do we apply that once we get this w? So now w into xk plus b, if this value is resulted in a positive, then we assign to the positive class, or otherwise we'll assign to the negative class. So the most important thing here is the support vectors. What are those support vectors? We have seen the examples that are on the boundary. So they have some special properties. We are interested in that. Why we are interested in that, and what what is the speciality about that is, so here you can see, so alpha k value can be either 0 or greater than 0, right? And when alpha k is 0, then in this whole W, in this weighted sum, so for that xk and yk, so that term will be 0. And for the remaining values, for whichever values of alpha k that is non-zero, only those values will be significant if you expand it, right? And so all the examples whose associated Lagrangian values are non-zero, such examples are known as the support vectors. And if you observe, so those examples are on the boundary of the margin. So those are the support vectors. So that is how we are interested in the examples whose corresponding Lagrangian values are non-zeros. So those are the support vectors basically. And now what are the advantages how SVM is better than the traditional linear classification models? Of course, SVM works relatively well when there is a clear margin of separation between the classes. Of course, perceptron will also do that. And SVM, what is the better advantage of it is, SVM is more effective when you have high dimensional data, and also